Sella. I'm first author and the student, the PhD student in this paper. So FEC, or forward error correction, we're going to talk about that and why I argue that FEC killed the cut-through switch. So first, short recap of what a cut-through switch is. Upper panel, you can see a store and forward switch. That's a regular switch. Lower panel, you can see a cut-through switch. The difference is the way they process packets. So a cut-through switch only has to wait for the header to come in, and you can start processing and switching the packet and already start releasing the bits. So forward switch has to wait for the entire packet to arrive before it does any switching, any processing, any releasing. So a cut-through switch is inherently faster. You can see that a cut-through switch releases the entire may release the entire packet before it can forward finish processing it. Just rough numbers, order of magnitudes. Switching latency for a cut-through switch would be less than 500 nanoseconds. Switching latency for store and forward would actually depend, to be honest, on the length of the frame. Roughly an order of magnitude larger. So why is latency important? I mean, who cares about latency? So the most tangible example is you try to load a web page, and the web page is too slow to load, and you just abandon it. Now, that is associated with revenue generating with ads, and you can take other examples like high-frequency trading and high-performance computing. So how do we get fast? We got along pretty fine up until 10 gigabits a second. When I say we got along fine, I mean we improved each time the atomic building block, which is the single physical link. Then roughly 2012, I want to say, 2012, we improved a little more by doing what we call parallelizing. So 4 by 10, we just took the 10 gig that we were good with, multiplied it by 4, multiplied it by 10, and got 40 gig, 100 gig. Parallelism, in a sense, is quite easy to understand because you just cram more wires into the same place. So you basically have to multiply the price of the single lane by the parallelism factor. Then we had to improve the atomic building block. We couldn't move we couldn't move forward any faster. We couldn't just drive the bits faster through the same wire. So we had to advance both where you see the line in the atomic building block, which is the single physical lane, and that always is accompanied by parallelism. So once we got 25 gig, we could make a 4 by 25 gig, which is a 100 gig link, et cetera, et cetera. And this is roughly when we started to need complicated forward error correcting mechanisms. And why is that? Or who needs FEC? Or why do you need FEC? So first I'm going to, just for those of you who don't know, just give an overview of what FEC is. So FEC in this case is a Reed-Solomon block code, and it consists, let's say, in a 25 gig case of 4,140 bits of data and 140 bits of redundant bits. So it looks a lot like a frame, and it is a frame, actually. It's associated with two things. You have to accumulate the entire block before you do any work on it, and then you start decoding it, which is also latency called decoding time. Now, this slide came to be when someone asked, okay, I don't know FEC, I don't know a lot about FEC, but what happens if we don't have it? And the question kind of didn't compute in my mind. I said, well, what do you mean you don't need it? What do you mean you don't have it? I mean, there's Shannon's theorem, there's capacity, there's higher bit error rate, you need to, and the person says, no, let's play it out. I have packets, I have errors. So on the other side, I have Ethernet frames and IPv4, IPv6 packets, and they'll probably catch the errors. And then we'll have transmissions, and that adds latency. And then I finally kind of figured it out. Okay, no, that's not what's happening here. So previously, we had low bit error rates, roughly in the order of 10 to the minus 16. You don't have to have fancy forward error correction for that. So what you could get is packet drop, meaning Ethernet CRC or IPv4 CRC or frame checksum catch up to 3 faulty bits and just drop the packet. What happens is 25 gig and higher order modulation, we relaxed the constraint on the line bit error rate to roughly 10 to the minus 6, and that's actually a nice number. So once you relax the constraint on that, let's say you opt for no FEC. So yeah, you get packet drops like you used to. You also get link drops, which you didn't used to observe as a user. But the nightmare scenario is actually false packet arrival. False packet arrival means that the packet has enough errors in it that it went through Ethernet frame checksum, it went through IPv4, IPv6 checksum, and you get silent data corruption. Tangible example of that is 20 years from now, you look at your web photos and you see they're not actually there. Another tangible example is money being erased off your account, et cetera, et cetera. So the idea is that this is not a new problem, and I'm quoting Tan here, right? It's a general phenomena of multiplexing or framing within framing or packets within packets. So you start with the blue packets, which you can think of as actual video frames. You compress them, you do whatever you do with them, and then you put them into the green frames, which could be DP or whatever frame you want to think about. Then you put them into other frames, and each layer adds more framing. Eventually, what we did is add more frames at the physical level. So a FEC block is just another frame, and that's something which is to remember. Linear block code FEC is just another frame. And that's the more general. If you understand this slide, the framing here, you can ignore the Reed-Solomon architecture. It's misplaced. If you understand that, the analysis is pretty much equivalent to other cases. So how does this introduce latency and jitter? On the upper panel, you can see 3 FEC blocks, 1, 2, 3. And you can think of the packet, the frame, the Ethernet frame, which is located inside the second FEC block, as aligned to the right, meaning the last bit of the 64-byte or small frame, the last bit of it is perfectly aligned to the end of the second FEC block. In this case, you can think of the first bit of this frame as experiencing no latency, or just latency of the frame itself, which it had to do anyway. We start sliding this frame towards the left. Oh yeah, and this is the least latency if we go forward, meaning this is the best case where you get a perfect alignment of the frame within the FEC block. To start sliding this frame within the FEC block, you get to the worst case scenario, which is the first bit of the frame is perfectly aligned with the first bit of the FEC block. In this case, you can think of the first bit of the frame has weight for the entire frame to arrive, but also for all the other bits in the FEC block to arrive. And that adds latency. So this is the first bit has to wait for the entire FEC block. This is the worst case scenario, as long as you have the frame within the FEC block. Then you have cases in which you have overflow. So one case of overflow is the header is still in one FEC block, the rest of the packet, the rest of the frame is in another FEC block. In this case, you have to wait for the entire first FEC block to arrive, decoded, and then the entire second FEC block to arrive, decoded, and only then can you actually do something with the packet. This is the worst case latency for storing forward. The final case is where you have the header itself being split over 2 FEC blocks. So the destination is in one FEC block, the rest of the packet is in another FEC block. In this case, even a cut-through switch gets hit because it needs the entire header before it can do something on the frame. So just to demonstrate and give you some numbers, right? These are the numbers for latency of worst case scenario is 25G FEC single lane. You can see here that for worst case scenario 100G FEC. Other numbers would show you how much for this is a 10 meter fiber optic latency. So we have a packet, the green triangle. We have a packet traversing the data center, and with each hop, it accumulates both red and blue latency. Blue is just the switching latency it had to take anyway, and the red is the FEC latency, which is the worst case scenario at 25, which it has to take now. The calculation on the upper panel shows that it's roughly the same order of magnitude. So we basically doubled the latency through a data center in this case. So this analysis is very true for cut-through switches. So you remember cut-through switches just need the header, and once they have the header, they can process it, they can do the switching over the packet, and they can release the data. So the worst case scenario for a cut-through switch is 226.1 nanoseconds. That's the red flat line. And that's the worst case scenario, meaning whatever alignment you have of the Ethernet frame within the FEC block, that's the worst case scenario for a cut-through switch. For a store and forward switch, that's not exactly the case. And why is that? A store and forward switch has to wait for the entire frame to arrive anyway. So you could say that the latency that we just counted here as blue, red, blue, red, blue, red, for a store and forward switch, it had to wait for the entire packet to arrive anyway. So kind of, there's kind of masking or kind of hiding of the latency because the bits have to go to the upper layer. If you remove that latency, or the double counting of the latency, you actually get that a store and forward switch outperforms a cut-through switch, or at least not as bad as a cut-through switch. So this is this case. Remember, you have the case where the FEC header is in one FEC block, the packet is in another FEC block, and for a store and forward switch, this doesn't really matter because it's counted anyway. So every time you see the number of the frame size approaching the size of a FEC block, you see kind of improvement in performance, which is actually just double counting of latency. So just to recap on what went wrong, right? We started by wanting to go faster, and we needed more complicated error-correcting codes or error-correcting codes. In order to, we needed forward error-correcting codes because we relaxed the constraint, we relaxed the demand on the line bit error rate to 10 to the minus 6. And if you don't use FEC, you get link drop and you get false packet arrivals. Then we got to a very old pitfall, which is framing within framing. And then you do the analysis just as you would for any other framing within framing. Future work, or what we would like to see as possible correction for this or possible implementation for this. So this was all written, the spec was written in 2012, 13, 14 for 25 gig, 100 gig, et cetera, et cetera. You have to consider that when the spec was written, the FEC targeted the worst case scenario link. So whatever materials they had there, whatever modulation options they had there, transceivers they had there, that's what the FEC is targeting. Now you can say, okay, but you know, some years have gone by, I'm buying more expensive, more premium equipment. Maybe I could get a discount on the latency I have to suffer because in 2020 they didn't have these materials. So the answer is not exactly. You can turn off FEC completely, but then there's no guarantee on what's going to happen. And you still have to suffer for latency. Future work would consider flexible FEC, which means I have an assortment of things. Some of them are performing well, some of them are performing less well. I will adjust probably, or I would like the ability to adjust FEC according to the link I have. Another thing to remember is latency, bit error rate could be traded. For instance, if you're watching a video, on Netflix, maybe you don't mind the occasional frame gone wrong, but you do mind latency. So maybe you'd like to say, okay, I'm willing to suffer bits in error, but latency is kind of for me. So you may, as a user, want to have that trade latency for bit error rate. Adjustable rate is another actually work being promoted by others. And the entire solution, I would name it SmartFi, which would include a FEC gearbox, meaning not just one or two options, but more of a, well, continuous, but several options to cover several applications, and a constant monitoring of frame error ratio and effective bandwidth and header latency estimation and mean time false packet arrival. And that all would go in a control box that would eventually change the FEC, et cetera, et cetera. That's it for me. Any questions? Yes.
Actually, why did you choose a Reed Solomon?
You mean the second?
Well, I mean, it's okay. It's open source. Anybody can download it. But for your problem, it's probably not the best code you could use. And I have a second question related to this: is why did you use a fee layer code and not move it up to the network? Since this is where.
Two different questions. I'm going to first one.
Okay. No, but actually, yeah, I think that they're related. But I mean, I would have pushed your problem at the network layer, and also I think the Reed Solomon, there's some stuff that is way better than that.
Perfect, thank you. Okay, I'm going to take second question. Okay, second question is actually, would you want to tackle the errors at the link level or at the physical layer level? Why do you not tackle at the application level? Great. Two answers for that. Now, let's assume I took Reed Solomon and I have a good reason for that. So reason number one would be there would be a lot of logic spent on correcting the errors. That's not good enough. Another reason would be if I relax the constraint on the bit error rate to 10 to the minus 6 or 10 to the minus 5, it's not clear that the packets would go through all the way to the application. In fact, it's not even clear the two MAC frames would not coincide due to enough bits in error. Brilliant. So just to clarify, Reed Solomon FEC was used by the Ethernet standard. These are Ethernet speeds, right? I'm actually arguing towards using different codes and multitude of codes and target-specific codes. I'm going to raise the question, if it's okay, on why did we use Reed Solomon codes when the spec was written? Is that well, that's a standard. That's yeah. So I'm trying to say the following. Okay, if you let me just rephrase the question as why they use Reed Solomon with okay. So the paper says, okay, so the paper argues, yeah, you don't have to use just Reed Solomon. You can use variants of it. You can use BCH, JLDPC, convolution codes, for instance. I argue to convolution codes at the expense of bandwidth, for instance. But yeah, I agree completely. I thought the question was on why did they use Reed Solomon in spec. The reason was DFE error propagation. Sorry. Okay. Other questions?
any other questions, we can thank the speaker, thank Omer, and give the floor to the next speaker, Alexander Clemm, who will have to set up the computer, so I have to entertain you for a while. The paper which is going to be presented is a new framework and protocol for future networking applications. So this is actually the second session starting right now. And there is the pointer if you want. So you have to connect the USB thingy. So without further ado, since the projector works, Alexander, the floor is yours.
Thank you. Good morning, everyone. I'm not sure actually if this pointer works. Oh, it does. It did. No? Wrong button. Okay, all right. Okay, I think we got it now. Okay, thanks. Yeah, so this is a joint work actually with a couple of co-authors. My name is the second author. So just to be having, I'm presenting on behalf of an entire team this new framework and protocol for future networking application. So in terms of, so why are we doing that? Basically, motivation for this is that new networking trends push the current internet technology to, in many ways, to its limit. I think everybody will be aware of this. And basically, there are aspects that are hard to achieve just with current technology. And basically, this concerns things such as the ability to provide service level guarantees that are both ambitious and high precision, so basically highly accurate on target values. Another challenge concerns the ability to simplify operations, to be able to rapidly program, introduce new networking capabilities, customize adapt these capabilities for different deployments and so forth. And also, there are a whole set of new services which are about to be introduced from virtual reality, augmented reality, internet, industrial internet, many applications of those sorts. There are, of course, so basically, there are many point solutions that deal with different part problems of this. However, this basically leads overall to a fragmented and fairly complex technology landscape. And for this reason, basically, what we have taken is basically we've taken a stack and seen basically can we think of a more holistic solution that rethinks basically this problem, unifies a lot of those problems and simplifies it. And basically some of the guiding principles, if you will, were that we want to get from a more best effort type of services towards a specific view towards also enabling service level guarantees, what we call higher precision type of services, the ability to customize and program the behavior of flows of individual packets, supporting of service level guarantees, and all of this while providing greater operational simplicity and visibility. And so this has led us to introduce Big Packet Protocol, or propose this, short BPP. And basically the idea here is that to provide a protocol in the framework of a company that allows to process packets and flows as they traverse the network, guided by information that is carried in the packet itself. So basically, the packets carry metadata and very simple commands. We'll see this in a moment. Injected at the edge to guide basically how the network, the forwarding devices, basically what they should do to act on those packets. Essentially, the type of things that are steered by this is force decisions, reservations, forwarding decisions, visibility, collection of telemetry data, all of those sorts of things. And there's an additional option in there that allows to also force stateful flow processing, by thinking of it as a programmable flow cache. Various benefits for this. Basically, from the providing of service level guarantees to being able to program the behavior of the flows by injecting, by basically adding this information at the edge. Doing this in a way that is isolated, so basically you can program your individual flow in your individual packets, not the device as a whole, not other flows and so forth. And you can do so, and in doing so, it's actually holistic. You can actually inject several commands, for instance, to address multiple concerns concurrently. And ultimately, the idea is to also allow, allow basically this guidance of the flows and packets without having to know or without having to make users aware of the underlying networking infrastructure. So basically, the networking infrastructure should be opaque to the user. The goal is really to basically to actually facilitate the programming, the customizing of the flow behavior. Okay, so there are a number of cornerstones of this: packets themselves, the stateful extensions, then the infrastructure on the node that enables all of this, and then finally the network operations that allows you to program this to convey the intent of the users, what they want to do, enable users to define the network behavior, the SDKs and APIs, and so forth. There's a lot of topics just for one single talk, so I'm going to focus mainly on the top topic, a little bit touching on the second topic. The other ones are important as well, but we simply do not have the time and space here. Okay, so so what does this protocol look like? And basically, at the core of this is the concept of a BPP block. BPP block is basically an additional piece of metadata, if you will, that we are inserting or attaching in the packets. The BPP has a header itself and a block which contains commands that guide basically the processing of the packet and a set of metadata. Typical length of this depends on the use case. Typical length would be 32 octets or 128 octets, just to give you a rough idea of what overhead and so on we're talking here. How this is carried is actually there are, well, we were looking at integration of different host protocols. So essentially the BPP header includes the pseudo header of the host protocol. So you could have an IPv4 or IPv6. You could also potentially use other protocols to carry the BPP block. What the BPP block header concerns? Well, a lot of different fields. I don't want to go through every detail of this, but I want to basically point out a couple of items here. Main thing is basically that whenever you introduce commands, you have, of course, to think of also what is the semantics of these, what do you do when things fail, how do you deal with timing constraints, with dependencies between commands, which is important to optimize the things. And there are different flags in the BPP block that basically indicate this and that guide this. For instance, there are a whole set of fields that deal with error handling support. For instance, what should you do if one of the OIP command encounters an error? Should you drop the packet? Should you continue? If there are errors, how do you report on them? How do you flag that an error has occurred? Do you want to have verbose information and so forth? Other timing constraints, if any, on the packet, etc. Then basically going into some of the command parts and the metadata parts. As part of the command, basically what that is, commands are always conditional, which basically means that we can have a set of one or two conditions. That say basically if a certain condition holds, and we'll get actually into an example of what those things would be, then basically I want you to perform a set of one or more actions selected from a set of action primitives from this. And there are the conditions basically refer to condition type. There's basically the function that is being Boolean function that is being evaluated for this. There are basically a set of built-in conditions that we foresee, for instance, comparisons, threshold comparisons, things of that nature. But there's also the possibility to extend the set of built-in conditions with your own proprietary conditions if basically the extension flag is being set. Similarly, basically for actions, there are basically a set of built-in actions that can be performed. There's the option to also extend the action set. What is also very important is, since there can be several actions, there are also flags that define whether, for instance, certain actions can be serialized or whether they can be performed in parallel. Basically, to allow for optimization of the processing of these. Okay, so what can be some of the conditions? Well, first of all, why do they have, maybe there's not a condition at all, so true is a valid condition, which basically means you unconditionally do something. But you can also check for the presence or absence of a state. You can match parameter values, you can compare parameter values with certain state on the router. You can, for instance, look at, for instance, information. You can compare, for instance, the threshold with, for instance, interface utilization on the router to affect your forward or to affect the collection of telemetry, as an example. You can basically check for certain conditions that hold that are valid for the flow as a whole. For instance, for information that you would maintain as part of your stateful extension, your statelet cache, for instance, to see what is the current delay that you're experiencing for a packet, for a flow, taking actions on these things, those sorts of items. Obviously, those comparisons or those conditions can be parameterized. So for the actions, well, you can select from a predefined action catalog. So this is not generalized programming language instruction. They are custom command, if you will. So you can, for instance, act on a packet. You can drop it. You can mark it. You can buffer it, etc. You can act on metadata. So you can basically write to the metadata that is carried also as part of the BPP block. You can modify it. You can swap the metadata with header information and so forth. You can act on state. If you support basically these stateful extensions, you can basically read to this programmable flow cache, if you will. We call them statelets. And you can have certain very limited actions on the device, and those are not device actions that reprogram the device itself, but you can, for instance, retrieve OEM information from the device. You can retrieve telemetry that is useful for operations, to debug, to troubleshoot your network, to optimize your network, and so forth. You can also manage resource reservations if you have the need to do this. And there are no actions to modify actually payload and to reprogram the device as a whole. So basically, these are things which are prohibited. This is basically important for our isolation property. All right, so basically in terms of, well, the commands can be parameterized. Essentially you can refer to a piece of metadata that is carried in the same BPP block. You can refer to certain data in the flow cache or in statelet for this, and you can refer also to data items on the node, such as, for instance, the queue depth and interface utilization and so forth. For output parameters, of course, the question is what this really means. Commands can basically define to carry certain output parameters as part of the metadata that is carried as part of the metadata block, or you can also write again to the statelet. Okay, in the interest of time, and go forward. So metadata, commands is one thing that can be carried in the BPP block. The second part is metadata. And metadata basically is used to guide the process, other data that is used to guide the processing short of commands. And you can have, for instance, information about the packet, tags, classifiers, assertions about the flow, and so forth. You can have certain declarative items where you don't give a command, but basically with surface level objective that you carry part of metadata, those sorts of things. Yeah. And the accounting information can carry actions as well. That is important for, yeah. Okay, so very briefly on the stateful extensions. I think I have a little bit of time to go for this. So basically, stateful extensions are optional, but they are useful actually for many use cases. And essentially, stateful extensions consists of, revolve around the concept of a statelet. And the statelet is a piece of on-device cache memory that you can basically think of as a glorified flow cache. But unlike a traditional NetFlow IPFix flow cache that's basically built in, you can actually program it, and you can basically indicate how to update it, what information to put in it. And for instance, an example of what you could put into this is you could put information about the service level objective for a flow. You could put information that is useful to measure service levels about the flow as a whole. You can put certain custom telemetry statistics. So just not, so you're not limited to your normal statistics that you would maintain as part of a flow cache. You can actually customize what you put in there, and okay, you can potentially find other applications as well. And the important thing is that basically with this information, you can also interact with the BPP packet. So the commands in the BPP packet can be used to write this data, to read from it, to match a value, to compare it as part of the conditions, and so forth. Obviously, with this, there are some state management considerations that do apply. For one, basically, especially on the node itself, or the infrastructure, there's a need to reclaim state cache that is no longer used. And also there need to be special facilities, or actually that can be supported with, to deal with, well, depending on your program logic, to deal with the ability to deal with packet drops, to deal with path changes, to also export the content of a stateless cache, to initialize this and so forth. Basically, the base structure is here. This is not a packet. This is basically a cache entry. Just to make this this distinction here. So you would have basically various metadata items that you can maintain here, and then basically certain additional housekeeping information, such as the key that is associated with a set of packets. Thank you. Metadata for last packet, expiration data, and so forth. Okay. Other consideration is mentioned. Okay, so this is all fine, but how do you put this onto the node infrastructure? Obviously, well, we don't really have time to go into this, but basically, part key of this, you need to have a BPP, your protocol engine needs to have the ability to support the commands. Ideally, you want this command engine to be pluggable so that you can extend it with new action primitives and types of data items down the line. This is a processing hierarchy that applies because not every packet needs to contain guidance for every aspect of what it is that you want to steer for this. And basically, you can think of when you have the standard forward behavior on the device, which can, however, be overridden by certain information that you're caching inside the statelet, which in turn can be overridden by the commands that you're carrying in the packet individually as you're processing this. The whole thing needs to be accompanied, obviously, with a new programming model and the SDK and API that allows you to customize this flow behavior. You want to be able to customize, program, validate the behavior of your tests. So we need to provide the facilities for this, and the frame provides this. And then finally, basically, there are obvious security concerns that different levels of security can be provided. In the interest of time, let's go through some of the things that you can do with it and how you would use it. So, as mentioned, you can basically make context-aware forwarding decisions that depend on various things such as the current service level, the current performance, relative absolute or relative to the service level objective, and so forth. You can carry a service level objective for this in metadata. You can store it in the statelet on the device. You can have various supports for measurement support that goes along with this, from delay to delay variation, etc. You can maintain the custom statistics about flows. You can take certain actions when certain things occur. For instance, you can say, for instance, do I want to drop a packet? It's late beyond repair, for instance. You can manage reservations of resources along the path that should you desire to, using the stateful exceptions. And implement service level dependent accounting schemes where you don't just count things, but where you count things based on whether the service levels are being met, continuously being met. You can aggregate and consolidate telemetry data for flows, which is useful for operational purposes and so forth. So very some use cases. So first use case is flow profiling. This actually goes very well with the earlier, I think it was his keynote on the classification of flows based on flow statistics or packet statistics and so forth that you can see. So there's basically, well, so flow profiling is a well-known technique. You can reduce for various types of operational insights. So think of this as a simplified picture. You can think of, for instance, profile or capturing basically the distribution of packet lengths of flow or of other statistics that are being observed during a flow. And these types of things can actually be very easily programmed and custom programmed using BPP. For instance, say, well, I'm interested in this data item. Here, obviously, my buckets that I want to have. And the algorithm is basically accomplishable using a single command that you put into a BPP pack for this. You need to have a stateful extension for this. And essentially you say, well, basically when you get a packet, you look at the target data, you select the bucket counter, you match the value, you increment and update the value in the stated, and you're done. And you can export it later on condition or on command. Secondly, basically mobile edge computing. It's also with one of the earlier here, where you could basically say, well, I have a server selection process that depends basically on my service level objective, the latency, etc. So how can I basically make a decision? Well, I use BPP to measure the current service level, carry the service level objective for this particular category of packet inside the path, and then based on this, I can make a dynamic decision based on service level objective and current delay, which server I route it to. In addition, I have various options to also combine the ability to jitter packets and so forth. We are basically out of time. I need to basically skip all this. I know KK is very interested in this. We can talk about this later. There's related work. We are different. And finally, basically, so in conclusion, basically the takeaways is basically what we're proposing is a new protocol and framework that enables high precision networking geared towards future networking applications. And the basic idea is to have program packets to guide this dynamic context-aware processing by the network for the flow. Many benefits, including service level guarantees, it's programmable from the flow edge, etc. And it avoids, it's a holistic solution. It avoids these fragmented points that are otherwise basically emerging. And it allows to do all this while keeping the network infrastructure opaque to users. So it's very easy to manage. Currently, basically, we have a proof of concept under development. Various future work items from in-house and domain security, account solutions, and refining issues of programming models and APIs for this. I want to mention also, so this is basically an active piece of research. We also welcome research collaborations. So the end. Thank you.
Thank you very much, Alexander. Do we have any question from, yes, at the end of the room?
So how do you handle deployments? I mean, because at the end of the day, there are lots of protocols, right? And the community always has, how to deploy it, how to coexist. Yeah, I mean, can you shed some light on this?
Sure. So we're not quite at the deployment phase yet, so we're still basically in the research phase. But basically, a couple of items for this. One basically is the question. Well, obviously, basically to support this, you need to support BPP, or basically the protocol. In terms of, if I go back here, basically what we are foreseeing is that in general, basically the host protocol. While we can use different host protocols, you would basically see to have a different ether type. For this. So basically, it is a new protocol that will need to be supported in order to deploy the individual logic and so forth here. The command sets, the action sets, primitives for these will be a set of commands which are just part of the general framework, which are basically presumed generally present. If you want to deploy your own custom extensions, you can do that obviously as well. But basically, for this, you need to have additional deployment support. So that we want to say, okay, if I have a new custom command that I'm implementing, indicated for this extension flag and extension identifier. For this one, basically, you will need to have separate deployment support, and the deployment support you could have will be similar to how you would extend the programmable switch and so on today. You need to deploy this on individual devices so that the new command can be plugged into the command engine and be understood. But yeah, so this is basically we have the hooks in there, but this is still early.
Any more questions? I have a question, and I invite the speaker to come here just to begin setup. I was wondering, how do you, let's say, merge your proposal BPP with the existing like SDN type of architecture, in which, the plane is supposedly changing, and you want to add the statefulness on top of basically the path that information follows has still some sort of, let's say, role in how you manage your programming.
Sure. So actually, there are several questions, I guess, associated with this. One thing, basically, the relationship to SDN. So this is basically different from SDN. But what it shares with is, of course, that the things are programmable. But in SDN, what you program is the network infrastructure. Here, you program probe behavior. We also don't rely on a centralized controller, which typically, at least conceptually, you would have in SDN. There are ways how you can complement it. Obviously, I think actually the deployment aspect, if you want to deploy new commands and so forth, that's basically something that you would potentially want to centrally administer and so forth. So I think that is something where SDN and this can be complementary. Sorry, can you repeat the question? There was one part of it.
Yeah, that answers my question. Thank you very much. Let's thank again the speaker. And in the meantime, we welcome Torsten Runge. He's going to present Open Carrier Interface and Open Source Edge Computing Framework. The floor is yours.
So, thank you for the introduction. And now I'd like to speak about the Open Carrier Interface. This is a new open source edge computing framework. My name is Torsten Runge, and this is a joint work together with my colleagues Marc, Koerner, Aurojit, Panda, Sylvia, Ratnasamy, and Shenker from UC Berkeley and the International Computer Science Institute. So after some introduction and motivation, I'd like to introduce the OCI architecture. This is a very new architecture, and we also have a prototype of this OCI architecture. And I would like to show you some preliminary evaluation results of this. And finally, I will conclude my talk with our main findings and also give a small outlook on future work. So today we have a lot of challenges in networking. As you all know, the growing amount of data, the number of users is increasing, and so on. And we also have ultra low latency requirements here, and especially for history automations, we have very tough requirements. Okay, I will give some examples later. So the idea is to solve this with the help of the edge computing. So edge computing is computing closer to the end users, you all know. And this also enables computation offloading. That means by this way we are able to offload applications to the network edge. And by this way we can achieve high bandwidth and low latency requirements. So, but this also allows to reduce the backbone internet traffic, because not every stream needs to be sent to the centralized cloud. Yeah, so we can do a lot of on the network edge and save so also bandwidth here. So, and here in this table you can see some common internet applications, and with this throughput and latency requirements. Here, especially, these one in bold are emerging applications which will come in the next year. So here, especially augmented reality and virtual reality have very high bandwidth requirements. But on the other hand side, we also have here new use cases in the industrial automation. And here we have very tough ultra low latency requirements that are less than 8 milliseconds. So, and this is quite challenging for today's network. Therefore, to cope with it, ultra low latency requirements, one idea is to deal with this with edge computing. Yeah, we did some measurements as a for the state of the art. So today a lot of things are used with done with cloud computing, and this measurement is done with a home internet access point. And here you can see is a typical round trip time to the next cloud location. In this case, it's Amazon AWS. And as you can see here, if we have this barrier of this 8 milliseconds, this is quite tough to achieve with cloud computing today. Therefore, we really need edge computing. And as you can see here on these, it's called CO Central Office. And this might be a good location for the deployment of edge applications to support low latency and so on. Therefore, only this central office, which is a network edge, of course, in a specific case here, is able to satisfy these requirements. So our solution here, which I like to present here, I like to give you a big picture of that, is threefold. So first of all, I'd like to introduce the open carrier interface for edge computing. This enables network service providers to extend their business model for open up their by opening up the interfaces to the network edge for authorized third-party application service providers. The second issue is that we like to propose a global configuration manager because of the network service providers require an integration, resource, and orchestration framework for the computing and networking setup of services. Finally, we also see here a paradigm shift from the traditional client-server model to an client-edge server model to support scalability, consistency, and resilience of these edge applications. So our vision is to have an open network interface for carrier networks. So in this case, the network service providers act as an edge computing provider by offering open carrier interfaces. This is so-called OCI. And yeah, to the network edge. So by this way, a third-party application service provider can deploy code on the network edge. By this way, the network service provider also is able to charge the application service provider as a tenant. So the network service provider get a new business model back from the simple packet forwarding we have today to a more pay-per-use model, yeah, for serving edge applications. Yeah, and by this way, the application service provider is able to deploy its edge applications without any networking knowledge, because of this is done by the service provider. So to become this vision true, the network service provider needs to open up the network edge for authorized third-party applications providers so that they can deploy their application logic on the network edge. So for this, we need the open carrier interface architecture. I'd like to present you this architecture in more detail. So this architecture consists of multiple parts. We have here our clients. Here's the application service provider which deploys third-party code, and we also have multiple other components. Here's the network service provider itself, which owns all this infrastructure. Of course, it's the network carrier owns the network edge, and it's his autonomous system. And yeah, by this way, we introduce here a global open carrier interface coordinator, which is a logically centralized component, which is a domain-wide. Domain-wide means that it's in the domain of the autonomous system of that carrier. So, and this provides an application service provider interface. This is a so-called open interface to deploy third-party applications. So, and if an ASP uploads code, application load code. This code is distributed via this global coordinator to the local coordinators, which are located on the edges. So the local OCI coordinators, they have only edge-wide scope, and they manage lists of the actively running edge services, IP addresses, their lifecycle status, and so on. And if a new customer arrives at the specific edge, then this client requests the local coordinator on that specific edge, and then this local coordinator needs to decide if there are left resources on that edge to be able to run this edge application. So there's an interaction between this local coordinator and the underlying resource and orchestration manager. A resource and orchestration manager is not in the scope of OCI. It's provided by another party. For instance, it could be an OpenStack infrastructure below or something else. But we need here, as this is a real resource manager of the edge, so it's got schedules the local edge resources like compute, network, and storage. And it also is able to allocate resources to other functions like functions we also have here. We have an NV manager, which of course shares these compute resources. So, and if there are spare resources left, then this OCI is able, or this local coordinator is able to spin up edge services to provide a better service for the client. So, but by this way, we need an adapter because we have specific commands. And resource and orchestration manager adapter is like a driver between the local OCI coordinator and the specific underlying resource manager. Yeah, it provides a generic interface to translate the local coordinator specific commands into specific commands of the underlying architecture or resource and orchestration manager. Overall, we also provide an open carrier interface library. And this is to provide methods or templates for the simple development and deployment of client edge applications. So this is usually used by the application service provider, which develops the application logic and so on. And yeah, by the way, this library is used by several components, and it supports the integration in the overall OCI ecosystem. So, for instance, the dynamic lifecycle management and so on. So now I'd like to focus on the edge services. How can they be implemented? Because this is done by the application service provider itself, and also have here some discovery service. I'd like to speak in more detail about that. Okay, we have different approaches to implement edge services. So an edge service could be a mandatory component or an optional software component. It really depends on the application service provider application design. So how to connect several clients with edges, how to connect multiple edges with the back-end application server. This way, we can have two different approaches how to implement application services. On the one hand side, it could be a traditional monolithic edge application, which is easy to develop, but the scaling is only possible by the replication of this entire edge service itself. In contrast to that, we also support microservice-based edge services, which have a distributed structure consisting of several microservices, and by this way, we have a better scalability because of every single microservice can be scaled individually. Optionally, we can have a discovery service, which is used to resolve a specific edge service instance. By this way, the client and the local coordinator request the is a corresponding discovery service, and a specific client redirected to a specific edge service instance. So by this way, we can easily support application load balancing, also to support multiple versions of a specific edge service. Yeah, so we can have an easy shift from a new version to an up-to-date version. Now I'd like to give you an example of the OCI ecosystem. Here in this case, we have 2 backend servers, and we also have here 4 edge servers. So on edge server 1, there's an application server for IoT, and on edge server 2, there's an augmented reality server. So and now the application service provider decides, okay, these are real challenging applications. We want to have to support better support for these services. And by this way, the application service provider uploads code to the global OCI coordinator by specifying specific application requirements, for instance, the required bandwidth, latency, but also the required compute resources as memory or CPU. And he also specifies where this specific edge service should be deployed. So for instance, this edge application should be only run in a specific region or something else, in a specific country. Then we define this. By this way, it should be only run on edge service 1 and 2. And there could be another edge service for augmented reality, which is only able to run on, or should be run on edge service 2. And when the client comes, only at this time, this code is running. And only at this time, the application service provider needs to pay for the usage of that resources. Otherwise, there's only code there, but it's not running, and it does not create anything for the application service provider. So we really consume your resources on demand when a client is arriving. So in the paper, we also propose multi-domain support. This is when you have multiple domains from different network service providers, and by this way, a client is able to use edge service a different network service provider network. So to do this, the global OCI coordinator needs to share this edge service between other, and yeah, we can do this in different ways. We can have here a proactive exchange between the global OCI coordinators. That means it's done on a regular basis, or it could be also be in a reactive way. So that means when there's a new edge service, or if there's a request of a specific edge service, then this edge service is transferred or exchanged between the global coordinators. And usually there's only one global coordinator per domain. Okay, now I'd like to give you some overview of the prototype implementation and some preliminary evaluation results. So here, this is our implementation. We implement here the global coordinator, the local coordinator, the resource and orchestration setup, and also this generic interface to connect with a specific underlying resource and orchestration manager, yeah, which in the end spins up the actual edge service. And if a client requests for a specific edge service, he does an edge service lookup, and on that way, if there are resources available, this client gets the IP of that specific edge service, and the data flow is just started. Okay, in the following testbed setup, we evaluated this prototype, which is done with the help of 2 servers. On the one hand side, we have a traffic generator, which represents multiple clients. And yeah, there might be multiple edge service requests, and yeah, which follow a Poisson distribution. That means we might also have bursts of edge service requests. Yeah, and yeah, additionally, we have another server, the edge node. Here runs the local OCI coordinator, and with it holds 100 up to 50,000 edge services. So, and then a specific client is requesting a specific edge service, and we measure the time, how long does it take to look up this edge service. So these servers are interconnected by a gigabit Ethernet switch. We used an 8-core modern CPU running at 2.6 gigahertz, 128 gigabytes RAM, 10 gigabit Intel network card, and we used then Linux for the runtime environment. So our first scenario, we have we conducted single query lookup time. So that means we do single queries, and between each query we have a random pause between 1.5 and 2.5 seconds to avoid caching effects. And yeah, the lookup time is in the mean is 0.9 milliseconds for up to 1,000 edge services. We see a minimal increase if we have more edge services running on the edge, but we assume that the ACSI support for 1,000 to 2,000 edge services per edge is sufficient for today's applications. We also did some load-based measurements. That means now really multiple edge service requests come in parallel or close to each other. So we have here the 90th percentile of the edge service lookup time, and we can see for up to 1,000 edge services we have 1.8 milliseconds. So for higher numbers of edge services, we see a constant lookup time of 2.2, 2.7, and 4.2 for low loads. Yeah, and there's an increase, of course, if the overload increases. So according to that figure, we can say that the OCI prototype performance is sufficient to 10,000 clients per, and this is a typical number of the central office subscribers per edge, and this is quite realistic. So to conclude my talk, we have designed and implemented an open area interface and open source edge computing framework. This enables the network service providers to act as an edge computing provider by opening up their interfaces. This is then a new business model for them because they can allow third-party application service providers to deploy edge services that then be executed on demand. Yeah, and this USA represents a unified abstraction for the edge computing by a generic interface to the underlying resource management system. Yeah, and our preliminary evaluation results indicate that the OCI performance is good enough to cope with the usual number of clients, yeah, if you compare this to the usual number of subscribers to the central office. So OCI opens and simplifies the usage of the network service provider infrastructure to support the evaluation and innovation of new networks. So just 1 minute, one sentence to the outlook. We want to focus on the orchestration of global orchestration of the edge resources to better support the scalability of edge services between edges and so on. We also want to look on the serverless edge computing, yeah, and really on-demand scaling of the edge services. And we also like to focus on the mobility of stateful edge services. Yeah, and this implies that we are able to predict and also to prepare stateful edge applications on the next edge before the actual handover. Yeah, this is the end of my talk. I'm happy to take some questions. Thank you.
Thank you, Torsten. Question on the front.
Hi, I have two simple questions. First one, when you talk about edge services, are they VMs or they are Docker containers?
So in the end, it really depends on the underlying resource. It might be containers, it might be virtual machines.
And your computations are based on VMs, or they are independent whether they're containers or VMs? The numbers you showed.
So they are independent of each other. So they come from different third-party application service providers. They only share the underlying resource.
Okay. And second question, how do you compare your work with fog computing platform?
It's very close to for computing. For microcomputing and edge computing, it's very close to each other. There's also some processing on the end nodes, but in this case we try to offload a lot load to the edge to save GPU and or to compute offloading and so on.
Another question in the back.
And performance isolation.
Comments about security.
So performance isolation and security, right? So okay, the edge services, you can think about processors or virtual machines or containers which run on a specific edge. So we rely on this underlying technology to have serial performance isolation. And so by this way we rely on these security techniques and so on. But we also introduce some, well, we only allow authorized third-party application service to process to deploy code. Yeah. No, not anyone else can deploy code, of course, on the network edge. This does not make sense for the carriers.
If I may ask one last question, sorry if there are more, but we need to also prepare the floor for the next speaker if the next speaker wants to install his laptop. So my last question would be, how does your scheme relate to MEC, multi-access edge cloud proposals which have been kind of submitted and discussed in the 3GPP kind of forums?
Yeah, MSC is part of the related work. It's very close to that. So in our work, we argue that we are more on the on-demand side here. So it's not really detailed specified in the MSC that an edge service really started on demand when a client arrives. It's not clear in the current specification of MSC if this is always running or it is only executed when a real server is coming. And we say, okay, we only execute this when a real user is there because of the resources they are limited. We can run all services for every time.
Okay, thank you very much, Torsten. Let's thank again the speaker. Yeah. And while Ravindran prepares his laptop, I would like to thank you all for attending this second session, Network Architectures for Emerging Technologies. The next paper, which is going to be presented, and I urge you to connect to the, is titled Attributed Core Network for Architecture for 5G Systems and Beyond. Yeah, it's booting. It's good. It's too bad that the plane stopped running behind us, so that would have been entertaining. Thanks for not subtracting property from the hotel.
Do you have power for?
Do you also have the USB port? Oh, it's okay. The presenter. So you have it?
Yeah.
Okay.
I don't have.
So if you put it full screen now.
Yeah, the problem is Kiran, you have power for the bell.
far away, not too much. So, without further ado, I hope. Yeah, I was wondering. It's attached. No, where is it? This is it. It's perhaps in the.
You can remove it.
Okay. So
And then USB.
it's too sophisticated. Okay, as I was saying, without further ado, let's welcome Ravishankar Ravindran from Huawei Research. And the floor is yours.
Yeah, thank you. Yeah, sorry, I somehow I got mixed up. I thought my session was later part of the day, so I was not prepared. So anyway, so this work is basically some work some collaboration we have been doing with WinLab on looking into some kind of new ways you can new kinds of radio access techniques as well as things you can do in the core network to improve basically meet some new requirements that is coming from the IoT side of things. It's a pretty kind of straightforward work. So the basic agenda here is, basically I will talk about the motivation for this work. The key idea here is to analyze the current 3GPP mode of working in terms of looking at some of the control plane heads and then how an anchorless based network design might help. And then we basically compare the two architectures. So basically, if you're saying that, okay, you have UEs connecting using this, using basically an anchor-based network architecture was one that's anchorless, and some user plane services that can be enabled, and some simulation analysis that's basically based on considering some large-scale data that has been taken from multiple sources. So the motivation here is I think mostly it's covered in the previous talks. Is in terms of you have many kind of new kind of challenges that has been thrown by the engineering study and then followed by the IMT and then the 5G, and there's been architectures that are being proposed as part of 5G to handle these different class of applications, what you call as EMAB, MMTC, and ULC. So the idea is that if you look into how the architectures, particularly the core network architecture of cellular networks, has kind of developed, it's been kind of quite rigid. Though we have most of it is because you have this. It's basically most of the EPC design is kind of an overlay design. So you have a bunch of user plane functions that's overlaid on top of a transport network, and this fundamentally basically leads to high control overhead. Again, the control overhead comes because of several functions that you have to execute as part of this 5G network, and the fact is that now you introduce things like GP tunneling, because of which you do suboptimal routing, and so because of which again introducing new kind of services become difficult. And but again, there is kind of new recent works in IETF. If you look into, been following it, they've been looking at 5G has come with its next generation core architecture. So there's been looking at how some of the new kind of routing or forwarding architectures like SRv6 or ELA, things like that, or even ICN is included as part of this, can be fundamentally used to improve or basically help to kind of flatten the network architecture. And we also had some work that's been submitted to within the ICN RG. They're looking into how ICN can be kind of enabled, considering current 3GPP's proposed network architecture for 5G. So this is a nice study that shows exactly a lot of the suboptimality that exists in current LTE networks. Fundamentally, it shows the basic study comes from it basically looks into how the different user population is being aggregated at different points, and the basic one of the outcomes is that most of these current LTE networks, like in this study is I think around 7 years old. Probably it might have been a little more disaggregated now, but at that time, some of us concluded that for much larger kind of networks like current US operators, you have like 4 or 5 or 4 to 6 P gateways. So you understand that any user traffic has to anchor through those kind of gateways, right? And of course, this also, in addition to that, in addition to the kind of the user plane kind of suboptimality, you also have a lot of things that happens in the control plane. So every time basically a device goes into inactive state and goes into a fully active state, then you have to go through this whole set of messaging that goes into orders of 21 messages to basically get it into the active state. So this is again the basic paper looks into how you could introduce anchorless kind of basically redesign the network so that where you have mobility as part of the whole network infrastructure itself, and that fundamentally leads to flattening the whole network architecture. And though, I mean, the basic thing about, one of the problems that we try to address here is the issue of mobility. And if you look into architectures like mobility first, that fundamentally takes mobility as a first principle of its design. And the fact that you have basically mobility first again uses things like secure IDs to connect devices to the network, and that gives you a way to actually a way for the to basically authenticate devices in the just right in the node base itself. It gives you a nice architecture to kind of to address a lot of the issues that we saw in the previous. Basically in either in 3GPP, 4G, or even 5G, that is pretty much in that direction. So as I said, so the conclusion is that it allows you to do kind of low latency kind of connectivity, and the user plane itself can be kind of stateless instead of carrying all the state that is related to GDP sessions. If you're really doing, particularly with all these IoT devices, then it also leads to another scalability problem. Of course, things like if you know, I'm not going to detail mobility first things. Any ICN architecture fundamentally allows you to do things like multi-homing and multicasting. So these are fundamental, basically delivered in the network layer itself. So this basically compares, you're basically going from something like what 3GPP defines using the 3 different phases of from the registration to a basic point at which you can start transmitting packets. You can simplify this the signaling. On the right hand side, what you have is how this control interaction can be simplified. So the first phase of the authentication phase remains the same. Sorry, not the authentication phase. The phase of basically connecting the access network remains the same, but the authentication, and then you have the authentication phase, which is again it could be based on the basically the persistent IDs. In case of mobility first, you would use the GUIDs to basically authenticate the end devices. And because now once you have these IDs and then you have locator split and something like mobility first would use their own GNRS infrastructure that is baked into the network to handle mobility, then the packets can basically flow through between the 2 devices without really doing all the things that's related to that you do in a typical 3GPP based architecture. So this is again on the control plane. As I said, you have a mapping that goes from the device ID to the locator space. And so, but one of the key things here is that so we have what we said is policy and charging kind of information. So if you look into 3GPP, a lot of the functionality there on a centralized gateway is also because you want to do policy charging, legal intercept, and QoS and all this kind of things. But now those things have to be kind of distributed, and now you have to handle it in a way that meets this operator's requirement, but at the node B level. So this paper doesn't kind of solve that problem, but so that's something that I think for needs more investigation. But the key thing, as I said, is that you have a nice clean architecture to meet most of the requirements that is met by that's required by the current 3GPP system. So here, I think the two use cases that we define, that we discuss here, is again basically showing the optimality of taking packets from one point to another. As I said, like it's an ID-based system. You resolve the packets at the edges of the network, you resolve it to the locators, and then you optimally route to the endpoint. So that's the voice of IP case. And then you could also introduce other services here. Basically, if once you have names, you have IDs, you can put policies, you can do service chaining. Say a packet needs to be taken through multiple middle boxes, you can do it. It would be simple encapsulation and decapsulation at edge points. So these are kind of services that is enabled by this kind of richer, kind of a more improved network architecture. From a simulation perspective here, as I said, like I mean, I think it comes from a few sources here. So the intra-domain topology comes from Kaida's study, and then you have the mobile insight that from which the connectivity characteristics of the endpoints have been taken, and then for basic guidelines on the 3GPP, the number of IoT devices that is going to be in the future. Say we have considered two benchmarks here. One is 2017 and 2021. So these numbers actually come from 3GPP. There is again probably the total number of UEs itself connected to a device, to an AT&T operator, for example, like AT&T also has some from, I think, something like OpenCell ID. So in general, the left-hand side would basically shows all the settings that was used for this more numerical study, and basically you can see the basic comparison in terms of the periodicity of devices, of typical smart devices versus something that an IoT device would do, and you basically it's quite you would relate to that kind of thing where IoT devices have much longer sleep cycles, and they have certain fixed pattern by which they actually connect and disconnect from the network. So here in terms of control plane overhead, so here again, this is considering what we studied in terms of saying that, okay, you have the entire, this huge network, considering some, I think there was some around a few tens of thousands of routers, and then you have this this 60 gateways, and then you have again you disaggregate the gateways to the S gateways, and then to the number of, and then you have UEs connecting, and then you divide the number of UEs among the number of S gateways, and this shows the actual amount of control overhead that you would have in comparing the EPC scenario versus something that happens in a distributed core environment. So you could see that, I mean, if you look into the total control overhead here at the MME, the fact that here again you're considering the case of purely three scenarios are being considered. So what you have is 2070 is basically the two. So one is 2070, 2021, and the other 2021 with IoT devices. So you could see the basic idea here is that if you have this whole set of devices coming in and basically kind of going on and off in terms of the periodicity that I showed you in the earlier slide, you could have around gigabits of giga packets per second kind of overhead at the MME level. At the same time, if you're doing something like distributed core kind of a network, as I said, with the ability to do authentication at the E node B level, and the fact that you have now distributed mobility state across all the routers, the per node cost of the control overhead comes down drastically. That's the comparison here. Again, this is something that probably you might expect in terms of the total hop length. As I said, like with EPC, you're basically having this issue with kind of spooning through the anchor points, but in this case you can directly route optimally between the 2 points. And that's the user plane in terms of number of the cost in terms of number of hops. Yeah, so the ongoing work here is to realize this, and again considering open air interface on the access level and doing a name resolution system, and actually studying this for large scale IoT scenarios, and basically showing the advantages of this architecture in terms of latency and some of the overheads that we studied earlier. Yeah, so in terms of in summary, as I said, like this is something that's, I mean, this work I would say is in parallel with some of the proposals that happen in the industry. As I said, IETF is looking into some of this thing. There's some study work items out from 3GPP2 in terms of flattening the network architecture. So this is, I think, this is basically in line with in some of the things that's going in industry as well. And we basically showed the kind of advantages that you get by having a flatter architecture by looking at the data sets that's publicly available. So that's it for my talk. Yeah, questions?
Thank the speaker. Thank you, Ravi. Any questions?
Yeah, I've got a question about anchor lists. So if the network has no anchor, so it's still not very clear how you do the lawful interception, charging, bidding, kind of things.
I said, like, you know, it would be distributed. I mean, if you really, I mean, the policies have to be distributed somewhere along, you know, Bs. And I said that's an open research problem. I said I'm not addressing that problem here, but the fact, on the contrary, if you're saying that everything is centralized, now you're having to deal with this kind of millions of IoT devices, that becomes another problem by itself. So you have to somewhere, this problem has to be addressed at some point, because if I look into all the 5 architectures, irrespective of all the, you know, the UPFs and all this thing, it's still tending toward the same LTE kind of architecture, and I don't think that's scalable. And if you're talking about slicing, and somewhere, you know, you need, if you're creating slices, they have to kind of either get rid of, do it on kind of new kind of network architectures, and in terms like getting rid of any kind of centralized kind of states as such in the network, or I don't know, you have to address it in one way or the other. So I mean, as I said, there's a tussle between the requirements and kind of the architecture you have to choose to meet those requirements. So
another question? I'm coming.
So I don't know if you already mentioned this, but what did you use for simulation?
Simulation is, I mean, it's simulation. So it was kind of looking into the idea was to look at the actual overheads, the average overheads and the max overheads on certain points in the network. So it wasn't. Yeah, but I think having said that, I don't know. Probably I don't know. I mean, because there's a piece on the distributor is based on mobility first. So I'm not sure if Shreyasee used any of mobility first simulation to study the numbers for the mobility first part, because the other one EP is fairly simple, but for this one was there the statistics come from saying that if I have this entire say from some 100 million device state distributed on all the routers in the network, then and probably that's also numerical. There's no real packet level simulation there, I guess.
Either 4G EPC or there are, but they're limited.
Okay. If there are no more questions, let's thank again Ravi. Thank you. And this is the end of the second session. The talks will resume at 2 p.m. And, well, there will be another chair that I don't know who's going to be. Enjoy your lunch and see you later.